Thanks. Thanks very much for the introduction. And I'm honored here to present our research on the acceleration of the transaction execution for Ethereum. My name is Andy. I'm the professor from Zhejiang University, China, and I'm also the co-founder of BlockSec. Before diving into the details of the transaction execution, so let me give you some background of the parallel execution. So what is the parallel execution? Why do we need the parallel execution? And what's the issue of executing the transaction in parallel? So as you may know or you may not know, the EVM is a single-thread program which only executes the transaction one by one. So if you have a couple of transactions inside the block, each of the transactions will be executed one by one. They cannot be executed in parallel. So suppose we have two transactions as shown in this slide, like the transaction T1 transfers the tokens from account A to B, and another transaction T2 transfers the tokens from account C to D. So actually, they can execute in parallel because these two transactions, they do not have any state dependency, right? So the state changes in transaction T1, they do not affect the state in transaction T2. But if the T2 transaction is trying to transfer the tokens from account A to C, then these two transactions, they cannot be executed in parallel, right? That's because the states changed by transaction T2 is affected by the transaction T1, so they cannot be executed in parallel. We have some formalized definition of the transaction dependency, but I will not go through all these formalization things. You just need to know if two transactions, the read set or the write set of the storages, they have some intersections, then we will say these two transactions, they depend on each other, so they have the transaction dependency. OCC algorithm is actually a very mature algorithm used by the database, for the concurrent execution. So the basic idea of the OCC algorithm is that we can first, if we have a couple of transactions that need to be executed, we can first execute this transaction in parallel, and then we need to validate whether these executed transactions whether they have some state dependency in the validation stage. So if they have some dependency in the states, then that means we cannot execute this transaction in parallel. But if we execute this transaction in parallel previously, so what we can do? We can abort all the transactions that has a state dependency, and then re-execute these transactions to avoid the incorrect result of the execution. So we have an example here. Suppose we have two transactions, as we shown before. Transaction T1 transfers the tokens from A to B, and another transaction T2 transfers tokens from C to D. So we can, so in the first, these two transactions, they can be executed in parallel. And after the execution of T1, we will do the validation to see whether there is any dependency on other transactions, and this validation can pass, and the state change will be committed. And for the transaction T2, we also perform the validation process, and this validation process can pass, and the state change will be committed. So after that, the state change of account A, B, C, and D, will be committed into the system, and they do not have any dependency. But if we have these two transactions, so for the transaction T1, the validation still can be success. That's because the T1 do not have the state dependency. But for transaction T2, the validation cannot be passed. That's because the read set of the account A has some state dependency with the transactions T1, right? So in this case, we cannot directly commit the state changes performed by the transaction T2. What we can do, we will abort the execution of transaction T2 and re-execute these transactions, so that because when re-executing this transaction T2, the state change performed by T1 has been committed, and we have the native states, right? So we can re-execute the transaction T2. So basically, if we have a couple of transactions and we use the OCC algorithm to paironize to executing this transaction in paironizelly, the speed up will depends on the conflict of these transactions. So in worst case, if each transaction has the state dependency with other transactions, so actually we do not have any speed up, but we will have even worse performance about the transactions, because we execute all these transactions and we re-execute the transactions. So the speed up depends on the number of conflicts during these transactions. So we can take a closer look of the conflicts of the actual smart contract execution. So let me use a real example of the ERC20 token smart contract as an example. So in the ERC20 token transfer, usually we will check the balance of the MSG sender to ensure the MSG sender has enough balance to transfer the token. So if we have a couple of transactions which transfer the tokens from the same account, this will create a large number of conflicts, right? Because they are reading the same states from the same account. And we perform some empirical studies. We use a transaction from January 1st last year to July 1st last year. We observe the conflict of the storage operations of these transactions. And we find that the access to the storage slots are not equally distributed, and they are obvious the hotspot of these storage slots, like 0.1% of the slots account for more than 60% of the access accounts. That means this hotspot storage, they will cause a large number of conflicts, right? So if we executing this transaction in parallel. So because of these conflicts, all existing the parallelism strategy are based on the transaction level dependency. That means if one transaction, the validation of one transaction fail, we will redo the whole transactions. And the real-world speed-up of existing parallelism strategies are limited by the trivial but frequent conflicts. So how can we solve this problem? In fact, we propose a new algorithm which do not re-execute the whole transactions, but we only need to re-execute part of the transaction inside, part of the operations inside the transaction to have a better speed-up. So what's the problem of the traditional parallelism algorithm? As I just said, the entire transaction have to be serialized due to a single storage slot conflict. So we can dynamically split the transactions into different types of operations. So we can parallelize the conflict-free parts of the operation inside that transaction, and we can serialize the conflicting parts, right? So by doing so, we do not have to re-execute the whole transactions when a conflict happens. So, because of this idea, we add another phase inside the validation phase. So if a subset of the read set conflicts, we only redo the related operations instead of aborting and restarting the whole transaction. This is the basic idea of our algorithm. So I can use an example to better illustrate our algorithm. So suppose we have a transaction T1 and a T2. So because the validation of the T2, they will fail because of the conflict, right, of the storage, the state of the account A. So in this case, because during the execution, we will perform extra knocks of this the execution. I will talk about what's the operation knocks later. But we have the operation knocks during the execution, and then we can redo the transaction T2. But we can redo the part. We can redo part of the transactions T2 instead of re-executing the whole transaction in T2. When redoing the operations, we use the latest value of the account A. The balance of account A is 90 instead is 90 instead of 100, and we will re-execute these operations, and we then commit the results of T2 inside the water state. So in order to redo part of the transaction, like in order to redo the operations of the transactions, we need to maintain the extra information when executing the transactions. We must maintain the operation log from conflicting inputs to the affected outputs. So let me use an example here. So suppose when we executing the transfer functions inside of the transaction, so because the transaction is executed, using the opcode, EVM opcode. So we need to know the value of the account, the balance of account A from the storage. So this is S node operation. So we have a shadow stake to knock all these operations. So each operation, each knock, each entry in the operation knock will record the opcode, operands, and the relationship between the output to the input. I will show you there. So for the S node operation, we will put an entry inside the operation log saying that this is S node instruction, and we will load the storage from the slot, and the value is 100. And this operation log, the index of this operation log is 1. Then we have the duple 1 operation. After that, we will have the greater than operation, because the greater than operation is used to compare the balance of the MSG sender to a fixed value, right? To compare the balance of account A to 10. So in this case, we will have another operation log, the operation log 2. The operation log 2 is greater than opcode. The opcode of this operation log is GT, greater than. The operand is 10, and the output of the operation 1, right? Because we need to compare the value of current account, current balance of account A to 10. And the current balance of account A is the output of the operation log 1, right? So we will put this information in the operation log 2. After that, we will have a jump I instruction, because this is a conditional jump, right? It will depend on the comparison result of the balance A and the 10. So in this case, we will replace we will add a property of the operation 2, because it's a constraint. We only execute the following instructions if and only if this comparison result is true. Otherwise, it will revert, right? So the entry 2 in the operation log is a constraint. It says that we need to the output of the operation 1 should be bigger than 10, and should be bigger than 10, should be greater than 10, and we can if we, only in this case we can continue executing the following instruction. Otherwise, it will revert. Next, we will perform a sub opcode. That's because we need to deduce the balance from the account A. So we will input the third the log in the operation log. So this operation log is a sub instruction. It will using the output value from the first operation, and it will deduce 10, right? So this is a third operation. And after that, we have the S star. We will commit our result to the address A. So by constructing this operation log during the execution, we can redo the part of the instructions when conflict occurs, saying when the validation of this operation fails, we can redo these operations, right? We can only redo these operations and use the nested value of the account balance A as 90 instead of the 100. So we can re-execute these operations, right? We can re-execute these operations. So this is the basic idea of the operation level concurrent execution of the Ethereum transactions. So we have implemented such a system on the Go Ethereum, and with around like 4K lines of code change. And we need to evaluate our system from two perspectives, right? One perspective is that we need to ensure the correctness of our system. So if our system performs some error result of the execution of a transaction into a useless, right? It cannot be used. So in order to evaluate the correctness of our system, we can replay all the transactions from the block 1 to the next block and compare the water state between our system with the vanilla gas client. So if there is any inconsistency between them, then something is wrong with our system. So it's easier, to perform the correctness validation. Another evaluation we have performed is the performance evaluation. We want to understand how much speed up can be achieved, using our operation level concurrency algorithm. And to perform this evaluation, we have replayed 5 million blocks from the 11 million to the 11.5 million blocks. And we use this, we feed these blocks using the vanilla gas and our system, and we compare, the execution time of all these blocks, all of the transactions inside of these blocks. And the speed up is around 4.28x speed up. So that means we can have around 400% speed up of the execution speed. And most of the blocks are accelerated by 2 to 7 x speed up. And we also have some optimizations of our system. We want to prefetch some storage slots when doing the execution. The prefetch optimization is not proposed by us. We just reuse some existing prefetch algorithm to speed up the EVM execution. And we use the same blocks, the same transaction inside the same blocks, and we can achieve around 7x speed up when we use our algorithm and the prefetch optimization. For the cost of our system, because we have maintained extra information right inside the memory, the operation log. So we have around 5% the memory usage increase because we need to maintain the operation logs for the stake. I didn't talk about the operation log for the memory, but we still maintain some extra information about that. And it's around 5% memory usage increase, so it's acceptable from our perspective. And how to use this our algorithm, or if we have optimized gas client, or what usage scenario can our system be used? I think first we can increase the block size if the gas client can be applied by our algorithm, because we can speed up the execution of the transaction, so we can put more transactions inside a block, so we can increase the block size. The second user scenario is that we can have a better MEV searcher. That's because when you perform the MEV searcher, you need to try to order the transaction inside the block to see whether there is a profit, what's the maximum profit when performing the ordering of the transactions. So you need to have a very efficient system to do that. So we can, if the MVA searcher, they can apply our system, I think they can have a better result with the same time. So this is two possible user scenarios. I think there are more user scenarios. So the takeaway of this talk is that the current transaction execution they cannot be synchronized, and the traditional parallelism algorithm like OCC is not effective because when there is a conflict inside the storage, the whole transaction will be re-executed. So we perform a fine-grained parallelism algorithm for the Ethereum execution, transaction execution called operation level concurrency. So instead of re-executing the whole transactions, we just re-execute part of the operations, part of the instruction inside the transactions when a conflict is detected. And we have implemented such a system, and our system can have like 4x to 7x speed up compared to the vanilla gas client. So this is because I'm a co-founder of BlockSec. BlockSec is a security infrastructure provider. We have a couple of tools and systems provided to the community. So I will not talk about too much about this. Yeah, this is half of the talk. Thanks very much.
Thank you. Are there any questions here in the room? There is one.
Thanks. I wanted to ask, from an ablation perspective, if you split the transaction into a part that is still valid and that has conflicting, you said that you improve over just rerunning the transactions, but did I miss why it's not just enough to rerun the conflicting transactions as a whole and not need to necessarily do all this complexity? I'm asking because actually, in 2017, we built a system at scale that did that, and I don't know why you'd want to go into the operations itself. I missed that. Could you explain?
Okay. So if I understand your question right, so because currently the EVM clients, they cannot parallelize the execution of the transaction, so they just executing the transaction one by one. So in order to speed up the direct solution would be we can borrow the existing concurrent algorithm like OCC from a database. We can run this transaction in parallel, and if there is any state conflict, we can re-execute the transaction using the latest state instead of the older state when you run the transaction in parallel. So our algorithm perform a little further. We do not need to re-execute all the transactions. We just need to re-execute part of the transactions to speed up the whole process. So this is the whole story.
Were your improvements numbers relative to the native sequential execution?
Yes, native sequential.
Or are they relative to the re-executing the transactions that? That's the relevant question, no?
Yes, thanks. So the number shown in this slide is compared to the vanilla gas, which means the transaction is executing in parallel. And for the OCC algorithm, like the re-executing the whole transactions, our speed up is around 2 to 4x. Yes.
We have time for one more question.
Yeah. How do you see the perspectives of merging this change actually into the Geth implementation? Are you aiming for this, and what could be the main roadblocks?
So can you say again? Sorry, I didn't get it.
What do you think about the prospective merging of your changes into the actual Geth client? Are you trying to do that? And what would be the main roadblocks or counter-arguments against doing this?
Thanks very much. So currently we just finished this prototype, and we have submitted a paper. And the next step is that we're trying to push our change into the official Geth repository and to see how the community responds to our change. Yes. Thanks.
Amazing. The time is up. Thank you so much, Andy.
Thanks. Thanks.